Section 3.5 is transformations of graphs. We're going to be looking at different ways that we can graph functions based solely on the transformations. Now, before we talk about this was not included in the lecture notes, but I feel like I need to start by giving you some parent functions, basic shapes of functions that we'll be transforming. I believe in this section of homework we focus mainly on the quadratic function, the square root function, and the absolute value function. Here is the basic equation for a quadratic function. It's y equals x squared. That's just a plain Jane quadratic function with no transformations at all. The square root function looks like this, y equals the square root of x, and then the absolute value function is y equals the absolute value of x. When we graph these parent functions, there's some basic points that we like to look at, and those are the points that will transform whenever we start graphing using transformations. So on a quadratic function, if x is equal to 0, y is equal to 0. If x is equal to 1, y is 1 because 1 squared is 1. If x is negative 1, y is going to be positive 1 because a negative 1 squared is 1. And if x is 2, y is 4. And if x is negative 2, y is still 4. We take these 5 points and then we connect them with a curve, and this gives us the graph of the parent function for the quadratic function. These points that I've got highlighted in red are the points that we will be transforming when we graph using transformations. For the square root function, the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and that gives us some points that we can transform. And if we connect those points with the curve, this is what the graph of the square root function looks like. For the absolute value function, the absolute value of 0 is 0, the absolute value of 1 is 1, the absolute value of 2 is 2, the absolute value of negative 1 is 1, the absolute value of negative 2 is 2. And when we connect these points with a straight line, we get this V-shaped graph that represents the absolute value function. So these are the parent functions that we will be looking at transforming as we go through this section. The first transformation we're going to look at are horizontal and vertical shifts. We use these two graphs to demonstrate the shifts or the translations in the xy plane. So here's our parent function for the quadratic function and for the square root function. I've already given you those. Now if we apply a vertical shift, we see that a graph is shifted up or down with a vertical shift. Vertical means up or down. The shape of the graph doesn't change, but we just slide every point either up or down, in this case 2 units. We take our quadratic function and we shift every point up 2 units. So this point that was normally at 0, 0 is now going to be at 0, 2. The point that was at 1, 1 is now going to be shifted up 2 units, and it's going to be at 1, 3. And then if we take our square root function, we can add 2 to it, and we see that our original function, our parent function, every point gets shifted up 2 units. So a vertical translation occurs whenever you have a constant outside of the parent function, and it moves, your shift moves with the sign. So a plus here will shift everything up. If k is some positive number, we add a constant to our parent function. That's going to shift this graph up k units, and this one would shift the graph down k units. So vertical shifts are outside of the parent function and they move with the sign. A plus goes up, a minus goes down. Horizontal shifts are inside the parent function and they move opposite the sign. So if I were to graph y equals x minus 2 quantity squared, what we see is we take our parent function that's in blue and it shifts every point to the right 2. Here we take our square root function, the parent function, and if I look at the square root of x minus 2, that shifts every point to the right 2 units. If I replace that minus with a plus, for example plus 3, we see that that shifts the graph to the left 3 units here, and it shifts the parent function to the left 3 units here. So what we observe is if we have a horizontal shift, the horizontal shift is going to be inside the parent function and it moves opposite the sign. So if we have f of x plus k, that's going to shift everything to the left k units. And if we have f of x minus k, that's going to shift everything to the right k units. So vertical shifts are outside the parent function and move with the sign. Horizontal shifts are inside the parent function and move opposite the sign. A minus will go to the right and a plus will go to the left. That's the opposite direction of things on the number line. So vertical shifts are outside of the parent function and they move with the sign. A plus goes up, a minus goes down. Horizontal shifts are inside the parent function and they move opposite of the sign. So a plus goes to the left, a minus goes to the right. That kind of summarizes the transformations for horizontal and vertical shifts for you. So to summarize, let's let f be a function, any parent function, and then let c be a positive number. If I have y equals f of x plus c, how will that affect the graph of the parent function? Does it move up, down, left, or right? It moves up c units. What about f of x minus c? It moves down c units. And then f of x minus c. It moves to the right c units. And f of x plus c. It moves to the left c units. So in example 1, we're asked to find an equation that shifts the graph of this function to the left 4 units and down 3 units. The left 4 units means that I'm going to have a plus or a minus inside or outside. It's going to be plus on the inside, and down 3 units is going to be minus on the outside. So if this is my function, my transformed function is going to have x plus 4 squared plus 3 times x plus 4 minus 1 and then minus 3. This minus 3 was my downward shift of 3 units, and this plus 4 right here took care of my shift to the left 4 units. Now I need to simplify this, and I get f of x equals 2 times x plus 4 squared plus 3 times x plus 4 minus 4. And you can leave your answer like that. There's no need to FOIL this out and distribute the 2 and distribute the 3 and combine like terms. You can type your answer like that into my math lab. You could write your answer like that on a test. Alright, in example 2, I ask you to write the equation that shifts the graph of the square root function to the right 1 unit, and then I want you to graph your equation. So for part A, what would the equation look like? Right 1 unit. This will be the square root of x minus 1. Now when I sketch the graph, I start by sketching my parent function in, and the parent function has these points at 0, 0, 1, 1, and 4, 2. And it'll look like this, just kind of sketching it in lightly. And then I take each one of those reference points and I shift it to the right 1 unit. So that gives me a point at 1, 0, 2, 1, and 5, 2. And that graph will look like this. You can do this on your calculator and it looks prettier, but it's important that you know how to do this by hand. Part B. We want to write the equation that shifts the graph of y equals square root of x up 3 units. What will that equation look like? Y equals what? Do I have anything under the radical with the x? No. What do I have? Just a plus 3 on the outside. So normally our parent function starts at 0, 0, has a point at 1, 1, and at 4, 2. And it looks like this. Then when I shift each of those points up 3 units, that puts me at 0, 3. This point at 1, 1 gets moved up 3, so that's going to be at 1, 4, and this point at 4, 2 gets moved up 3, and that's going to be at 4, 5. So the graph of the function, the transformed function, looks like this. Any questions? Horizontal and vertical shifts are pretty straightforward. Vertical shifts are outside, they move with the sign. Horizontal shifts are inside, they move opposite the sign. We can combine the shifts to do more than one thing at a time. Shifts can be combined to translate the graph of y equals f of x both vertically and horizontally. Here we're looking at a picture where we shift the graph of y equals the square root of x to the right 2 units and down 4 units. We start with the parent function, and then this blue function gets shifted to the right 2 units. This is the absolute value function. And when we shift it to the right 2 units, it just slides everything over. And then when we shift it down 4 units, our final graph would be this green graph right here. You can do multiple transformations. When you're graphing these, you don't have to go through the process of graphing all of the individual transformations. I just think sometimes it helps to see how they take place, where we go from the blue to the red with the horizontal shift, and then from the red to the green with the vertical shift. On example 3, I want you to write an equation that shifts the graph of the quadratic function left 2 units and then downward 3 units. Is that left 2 units going to be inside or outside the parent function? So we have f of x equals, open parentheses, x, is that going to be plus or minus? Plus 2 squared, and then down 3 means I'm going to do what outside? Minus 3. Normally your quadratic has these reference points. And now I take each one of these points and I shift them to the left 2 units and down 3 units. So that's going to give me, the vertex is going to get moved right here. This point gets moved to the left 2 units and down 3 units. So that's going to be a point right here and then here. And that's really enough to sketch your graph in. And this would be the graph of the transformed function, f of x equals x plus 2 quantity squared minus 3. If we did this on our calculator, I would first want to start by graphing my quadratic function, the parent function, and then I'll put in the transformed function in red. So this is going to be open parentheses x plus 2, close parentheses squared, minus 3. And you can see the graph of your parent function and then the graph of the transformed function. And that's a prettier picture than what I'm able to draw freehand. Now we also are able to stretch and shrink our graphs both vertically and horizontally. If you have a point xy on the graph of your function, then the point x of c times y lies on the graph of some constant times your parent function. That c there represents a vertical stretch if c is bigger than 1. If c is in between 0 and 1, it's a vertical shrink. And we can see that by looking at the graph of the square root function. This is the parent function without any transformation on it. And we have the points at 0, 0, 1, 1, and 4, 2. If I multiply the parent function times 2, what I'm looking at is the graph of y equals 2 square roots of x. And you see how I multiply each of these y values by 2. My x's are originally 0, 1, and 4. When my x's stay the same, the y's are now doubled, 0, 2, and 4 instead of 0, 1, and 4. And when I sketch that graph, you can see that what we have is a vertical stretch. So if that constant outside the parent function is bigger than 1, it's a vertical stretch, meaning your graph will be taller and skinnier. If that number is a proper fraction between 0 and 1, we see a compression or a shrink. So our x values stay the same, but the y values are now half of what they were on the parent function. So if that constant is in between 0 and 1, you have a shrink, and if c is greater than 1, you have a stretch. And all you're doing is you're multiplying the y values of the parent function by whatever that constant is. With the horizontal stretching and shrinking, it's going to be the opposite or feel the opposite of what the vertical stretching or shrinking was, just like the horizontal transformations felt like the opposite of the vertical transformations. If you have a point xy on the graph of your function, then the point x divided by c, instead of multiplying y by c, we now divide by c. We divide x by c. That point will lie on the graph of the function where my constant is inside the parent function now. I multiply x inside of the parent function by c. If c is bigger than 1, we have a horizontal shrink. That's the opposite of what it was before. We had a vertical stretch if c was bigger than 1. Now we have a horizontal shrink of this graph. And if c is in between 0 and 1, we have a horizontal stretch instead of a shrink. So what we see here is for these x values, negative 2, negative 1, 1, and 2, our parent function has y values of 3, negative 3, 3, and negative 3. And we just connect the dots here. This is the parent function. If I multiply the parent function by 1/2 on the inside of the parent function, I'm multiplying x by 1/2, what we see is a horizontal stretch. So the y values stay the same, but now the x values are doubled. And over here we see a horizontal shrink if I multiply the x's inside the parent function by 2. And if I look at the original x values, what I'm doing is I'm taking half of these numbers, and that's how I get these numbers here. So let me see if I can summarize this. So if we have y equals c times f of x, where c is a constant outside the parent function, this is going to be a vertical stretch if c is bigger than 1, and it's going to be a vertical shrink if c is in between 0 and 1. C, if you'll notice, is outside of the parent function, and in this graph the x's are going to stay the same as they are in the parent function, but to get our new y values we multiply the original y's by c. With the horizontal stretch, your constant's going to be multiplied by x inside the parent function. This is going to be a horizontal shrink if c is bigger than 1, and a horizontal stretch if c is in between 0 and 1. So c is inside the parent function, whereas on the vertical stretch it's outside the parent function. On the horizontal stretch, the x's are divided by c and the y's stay the same, but on the vertical stretch the x's stay the same and the y's are multiplied by c. So it's kind of the opposite thing going on here, just like it was with the horizontal and vertical shift. In example 4, I want you to use the graph that I have provided for f of x to sketch the graph of each of the equations. In A, we have y equals 2 times f of x. Is this going to be a horizontal or a vertical stretch? It's going to be vertical because the 2 is outside. So do I multiply the x's or the y's by 2? Look at your notes. I multiply the y's by 2. So here, this point at negative 2, 2, the y gets multiplied by 2, so that's going to give me a point at negative 2, 4. Here's a y value at 0, negative 2. That point now gets moved to 0, negative 4. And this point at 2, 1 gets moved to 2, 2. The point where I cross the x-axis, y is actually equal to 0, so the graph of the transformed function right here is also going to have the same x-intercepts. At this point, we just sketch a straight line, and I need a straight edge. And this would be the graph of the transformed function. And you can see how it's a vertical stretch. We've stretched everything vertically. On this one, the 2 is inside the parent function now, so this is going to be a horizontal stretch or shrink. Shrink, because it goes opposite. To get the new points, I divide my x's by 2 now, and the y's stay the same. So to graph these points, I look at my x here at negative 2, 2. The y is still going to be 2, but my x value is now going to be divided by 2, and negative 2 divided by 2 is negative 1. So I have a point right here at negative 1, 2. The y value stays the same. This x value gets divided by 2. I have a point at 0. That point stays the same. 0 divided by 2 is still 0, and then 2 divided by 2 is 1, so that point goes right here. This is a point, it's not marked on here, but it's at negative 1, 0. That point's going to move to negative a half, 0. And that will give me enough points that I can kind of sketch in what the graph of this transformed function looks like. So you see how it's a horizontal compression because this number is bigger than 1. The 2 there is bigger than 1. So this one was a horizontal shrink, and this one was a vertical stretch. This is something that you need to commit to memory. These transformations need to be memorized. I'm just going to assume that you know how to do them. Another type of transformation, in addition to just sliding up or down or stretching or shrinking x's and y's, we can also reflect a graph across both the x and the y axis. If the negative is in front of the parent function, then we have a reflection across the x-axis. If the negative is inside the parent function, that gives us a reflection across the y-axis. So on part A, we're asked to write an equation that reflects the graph of this function across the x-axis, and then we want to graph the equation. What does the graph of this function look like? This is a quadratic function, but how is it shifted? It's shifted down 1. So the parent function here, or this function, would actually look like this, would it not? This is the graph of y equals x squared minus 1. If I were to flip this graph across the x-axis, instead of having a minimum at 0, negative 1, I have a maximum at 0, positive 1, and our graph would open like this. But how would I express this function? Well, because it's a vertical shift, what I would do is I would multiply this function by a negative 1. And when I do that, I can distribute that negative, and that means that I have a negative x squared and a positive 1. So this graph is actually y equals 1 minus x squared. To have a reflection across the x-axis, you need to multiply the entire function by negative 1. For part B, we have f of x equals the square root of x plus 1. What do I do to this function in order to have a reflection across the y-axis? I multiply the x by negative 1. This graph is the graph of a square root function that shifted how? To the right? To the left 1 unit. So it looks like this. This is y equals the square root of x plus 1. This now takes this graph and reflects it or flips it across the y-axis. So instead of having a point right here, I'm going to have a point right here, and it's going to open up this way. This would be the graph of y equals negative x plus 1. So we can combine transformations. Transformations of graphs can be combined to create new graphs. For example, the graph of this function, y equals negative 2 times the quantity x minus 1 squared plus 3, can be obtained by performing 4 transformations on the graph of the parent function, which is the quadratic function. When I do this to the graph, how does that shift the graph? How many units and what direction? So it goes 1 unit to the right. And then this 2 right here does what to the graph? It vertically stretches the graph by a factor of 2. And then when I put this negative in front right here, what does that do to the graph? It reflects across the x-axis. And then when I put that plus 3 on there, what does it do to the graph? It shifts the graph up 3 units. In the last example, I ask you to describe how the graph of each equation can be obtained by transforming the graph of y equals the square root of x, then graph the equation. On part A, what do we do to the graph of y equals square root of x? What does that negative 1/2 do? Reflects across what axis? So it reflects it about the x-axis, and it's a vertical shrink by a factor of 1/2. So this would be the parent function y equals the square root of x. I've flipped this graph across the x-axis and cut the y values in half. This will still be at the point 0, 0, but instead of this point being at 1, 1, where will it now be? It'll be at 1, negative 1/2, because I reflect across the x-axis and I cut the y's in half. Instead of this point being at 4, 2, it will now be at 4, what? Negative 1. And so this is what the graph would look like for y equals negative 1/2 the square root of x. Alright, look at the transformations on part B. What does this minus 2 inside do? Shifts to the right 2. What does that minus x do? It's inside the parent function, so it reflects not across the x-axis, but across the y-axis. And then that minus 1 moves it down 1. So here's the graph of the parent function, and now I'm going to shift every point to the right 2 and then reflect it about the y-axis and go down 1. So when I flip this across the y-axis, that means my graph is going to look like this, but now this point that's normally at 0, 0 is going to go to the right 2 and down 1. The reflection first, and then I'm going to go to the right 2 and down 1, and that's going to put my graph right here. You always want to do the horizontal shift first. And we see that our graph will look like that. We can verify this or check it on our graphing calculators. When you type this into your calculator, make sure you use the negative here instead of the subtraction sign. You'll get an error message if you use a subtraction sign in front of the x. You've got to use the negative. And then we look at the graph. There's our first function and then the second function. Let me zoom in a little bit and get a better picture. And so you can see that it looks like this. This wraps up section 3.5. I guess one thing I can do is I'm going to summarize every transformation that we've gone over so that I can give you something that you can put on a note card that has every transformation in it. And I've done this in the past and it seems to be helpful. I'm going to leave the horizontal stretch off of this because we don't do it that often. Okay, so if we have y equals negative a f of negative x plus h plus k, this negative out in front of the parent function indicates that you have a reflection across the x-axis. This constant a is going to be a vertical stretch if a is bigger than 1, a vertical shrink if a is in between 0 and 1. F is just your parent function. It could be a quadratic function, absolute value, square root function, cubic function, whatever. If you have a negative in front of the x inside the parent function, that indicates that you have a reflection about the y-axis. If you have a constant added or subtracted inside the parent function, that's going to be a horizontal shift and it's going to move opposite of this sign. So a plus will go to the left and a minus will go to the right. If you have a constant added outside of the parent function, that's going to be a vertical shift and it moves with the sign. A plus is going to go up and a minus is going to go down. Now this summarizes almost all of the transformations that we talked about today. I would put this on a note card and carry it around with you, and whenever you have a spare minute, it's a study, just pull it out and look at it. And this wraps up section 3.5.